Welcome to this explainer. Have you ever stopped to wonder how a high-definition video just streams instantly to your phone, seemingly out of thin air? Or how millions of calls are happening all at once without wires getting crossed? Well, it's not magic. It's actually the incredible science of microwave communication and cellular backhaul. So let's jump right in and uncover this invisible, high-speed infrastructure that literally powers our daily lives. Here is our roadmap for today. We'll start with the basics of microwaves, move into powering the telecom backhaul, look at FDD, TDD, and alignment, check out some essential BTS hardware components, and finally, do some real-world troubleshooting with a VSWR alarm. All right, Section 1, the basics of microwaves. Okay, let's dive right into this. At its core, microwave communication is the transmission of information using radio frequency, or RF, microwaves. When we say microwaves here, we're talking about electromagnetic waves with physical wavelengths ranging from about 1 meter down to a tiny 1 millimeter. And frequency-wise, that corresponds to a massive range between 300 megahertz all the way up to 300 gigahertz. You can really think of these frequencies as high-speed expressways up in the sky, specifically designed to carry just colossal amounts of digital traffic. Now, to deliver that kind of massive data capacity, microwaves operate at a much higher frequency range than your traditional radio. But there is a catch. They absolutely require a clear line of sight, meaning no mountains, no skyscrapers getting in the way. Because of this, they're perfectly suited for point-to-point communication links, where data is beamed directly between two fixed spots. This makes them the undisputed champions for backhaul connections, moving super heavy mobile data reliably over long distances. Moving on to Section 2. Powering the telecom backhaul. You can think of backhaul connectivity as the network's spine. It's this vital, high-capacity link that enables the base transceiver station, the core network, switching centers, and all the other infrastructure to actually talk to each other. See, the data generated by your mobile device needs to be transported from the local cell tower straight back to the core network. Without this microwave backhaul acting as the spine, all the data your phone sends to that local cell tower, it would just sit there. It would literally have nowhere to go. And this brilliantly illustrates how backhaul handles complex setups. Take an indoor building solution, or IBS. It routes multiple RF services from one central base station out to remote units across several large structures. Microwave links provide that high-capacity, highly reliable connection to ensure that every single floor and every single building gets the data it needs without dropping a single packet. All right, Section 3, FDD, TDD, and alignment. Remember how we just mentioned that microwaves require a strict line of sight? Because of that, the physical setup of these networks is incredibly unforgiving. Microwave alignment means that both the near-end and the far-end antennas must be perfectly, physically aligned for point-to-point communication to actually happen. If a heavy windstorm knocks a dish even a fraction of a degree off its axis, the connection drops. The network relies absolutely on these antennas looking each other directly in the eye. So, once they are aligned, how do they communicate bidirectionally without their signals just crashing into each other? Well, engineers slice up the spectrum using two pretty ingenious solutions to this traffic problem. First is frequency division duplex, or FDD. Here, the spectrum is divided into distinct radio channels, each typically with a 200 kilohertz bandwidth, so you get one channel for uploading and another for downloading. Alternatively, we have time division duplex, or TDD. This is where a single channel is divided in time into 8 separate time slots to be used as logical and traffic channels for the users. Basically, FDD separates by frequency and TDD separates by time, but both beautifully manage the flow of data. Let's zoom in a bit for Section 4, essential BTS hardware components. Down at the physical tower level, the first absolutely crucial component is the duplexer. This is a specialized device used to connect the antenna system with the transmitter while safely separating the transmit and receive signal paths. Essentially, a duplexer acts as a critical traffic cop for the data. It allows a single antenna to both send and receive simultaneously without the high-powered transmit signal completely blowing out the highly sensitive receiver. It literally prevents the entire system from getting its signals crossed. Next up, we have the TMA, or Tower-Mounted Amplifier. And let me tell you, this piece of hardware is an absolute lifesaver for cell coverage. It maximizes the site's radio sensitivity by compensating for uplink feeder losses. I mean, think about the weak signal coming from your tiny mobile phone trying to yell at a tower miles away. By reducing the base transceiver station noise figure, the TMA dramatically improves overall sensitivity. It amplifies your weak signal right up at the top of the mast before it has to travel all the way down those long cables to the base station. Now, what's really interesting about this is visually anchoring those abstract concepts onto the actual hardware. You've got the TMA positioned right up high near the antenna, you've got the jumper cables, and then those thick feeder lines running all the way down to connect to the actual base station equipment cabinet below. This is the physical, tangible tower infrastructure that makes mobile communication a reality. Okay, let's get into the real world. Section 5, troubleshooting the VSWR alarm. Picture this setting. It's a Monday morning site visit to a casino in Lancaster. The engineering team has just laid down new feeder cables, DAS cables, for an indoor building solution. They power up the system, but suddenly, bam, they get hit with a stubborn VSWR alarm on the Airtel 3G network. Now, VSWR stands for Voltage Standing Wave Ratio. An alarm here often means energy is bouncing back down the cable instead of radiating out, which usually points to something like water in the conductors or damaged cables. So the team starts with standard troubleshooting, assuming it's a physical issue, right? They cut the cable, they clean the connectors, swap the jumpers. But when they retest it, the VSWR alarm kept screaming. That prompted them to dig a little deeper and recheck the physical port on the remote radio unit, or RRU. Ultimately, they realized they had to perfectly match the specific ports with their corrective 2G and 3G frequencies. So the big takeaway for the team? That persistent alarm wasn't just a bad cable, it was a strict requirement to verify port and RRU frequency matching during fault resolution. Which brings us to an incredible realization to wrap up this explainer. If a single mismatched frequency port on a piece of tower hardware can completely bring down a high-capacity cellular network, just how fragile is the invisible infrastructure we rely on every single day? It takes an astonishing amount of precise engineering, perfect physical alignment, and relentless troubleshooting to keep our world seamlessly connected. So the next time you stream a video, take just a second to appreciate the complex highway of microwaves making it all possible.